So my name is Carolin Crawford, and I'm the Public Astronomer here at the Institute of Astronomy in Cambridge. And today's Darwin lecture is Viewing the Universe, where I'll be looking at all the new facilities and telescopes that are coming online, perhaps over the next decade, next couple of decades, and hopefully previewing some of the exciting science that they'll enable us to discover.
So good evening and welcome to the sixth of this series of Darwin College lectures on the theme of vision. So, as you can see, it's twinkle, twinkle, little star, how I wonder what you are. That's one of the first science questions of children here, age 2 or 3 years old. I'm not going to sing it. But the question, though, is in one language or another. It's as old as science itself. It's as old as our measurement of time. And we still follow the Babylonian astronomers' example by numbering time and angles to a base of 60. 60 seconds, degrees. 60, of course, is nicely divisible by 2, 3, 4, 5, and 12. But how I wonder what you are. That question kind of shapes us, and through the ages, almost our visions of the universe has shaped our vision of ourselves and our society. So think about Pythagoras, Socrates, Plato's visions of the power of maths in understanding the movement of the planets. Or Paul on the Hill of Mars in Athens, quoting the vision of the Greek poet astronomer Aratus, or Galileo's vision shattering those crystal spheres. The Earth is not at the center. Then that fearsome vision in our time from NASA, Earthrise, seen from the moon, our tiny blue planet in a sea of darkness. So, for tonight's lecture in this series on vision, we turn to that question: where are we? What surrounds us? What is our place in the cosmos? How has our view changed in recent decades? And what changes are likely to come? So this evening, to speak to us, we have the Public Astronomer at the Institute of Astronomy here in Cambridge. So please welcome Dr. Carolin Crawford, who will speak, as you can see, on viewing the universe. Carolin.
Thank you very much. So as Mary's told you, the theme this evening is astronomy, views of the universe. And I don't often have to justify why I love astronomy and space and everything in it. But if somebody does push me and challenge me on it, one of the things I tend to trot out is that astronomy is the opportunity to study how the laws of physics behave, the fundamental laws of physics behave in extremes. An extreme conditions, say, of distance or time and sheer number of objects, or if you like, extreme physical properties of temperature, pressure, density, mass, gravity. And this is all kind of things that we can't do in the lab. So we're testing the laws of physics in a way that you can't do in your ordinary laboratory conditions, which means that we have to have a different methodology. We can't have the experiment and the control that most scientists might use. And this means astronomy is, curiously, almost like a passive subject in some ways, in that all we have to work with about the universe beyond the solar system, we're getting very good at exploring the solar system with robotic spacecraft, but anything beyond that we only know about because of the photons of light that happen to fall our way. And everything we know of the wider cosmos depends on our ability to collect, to analyze, and interpret that light, and how it's been radiated, reflected, absorbed, refracted. And so for astronomers, it's very true that all we have to work with is literally the views of the cosmos. Now, for ancient people, what they could see of the cosmos, ancient cultures were limited because their only observational tool was the unaided eye. You can learn an amazing amount with the unaided eye. You can see about 6,000 stars across the sky, from the very brightest to ones that are about 100 times dimmer. And not surprisingly, you knew about the star patterns, stars and their fixed constellations. They knew about the sun, the moon, and 6 planets, including Earth. So that goes out to and including Saturn. And their view of the cosmos ended up being very Earth-centric. Again, not surprising if this is where you're based and you're just looking out. And this is Earth-centric both metaphorically or sort of figuratively, in terms that the heavens are telling something to humanity. And here you have them marveling at the star, Halley's Comet, just before in the Bayer Tapestry. But the appearance of the heavens not only told us the calendar, but it also told us perhaps omens and messages from the gods to humanity, especially if you were lucky enough to see a giant comet in the sky. And also, literally, as you heard last week from Carlo Rovelli, they placed the Earth at the center of the solar system, with the sun and the stars and the planets and everything rotating around the edge. And this picture of our universe held sway for millennia. And the first real new astronomical data didn't come along till Galileo turned, a very crude telescope, but was the first one to turn a telescope to the skies. Now, again, you heard last week how his view of how the moons of Jupiter revolve around the giant planet, also how the phases of Venus change as it moves closer and away from the sun, basically ousted Earth from this special position of the center of the solar system. He discovered many things about the heavens, but the one that's probably most relevant for this evening's talk is the fact that he discovered when you look through a telescope at what would appear to your eye to be a blank bit of sky, you saw more stars. This is a page from his Starry Messenger, and he's drawn the constellation, the asterism of the Pleiades, the Seven Sisters. And the ones that he's marked by a star, and I've colored in blue, those are the stars you see with the unaided eye. And you can see this comparison to a more modern photograph, of course. And all the rest of the stars are ones that you would not know exist unless you look through a telescope. So this is quite a step change, realizing there are other objects out there beyond what could be seen with the unaided eye. You'd only see them through a telescope. And this opens the doors. You get huge amounts of innovation in telescope design and detector. You're still using your eye as the detector, but telescopes improve. And we learn more and more about the cosmos. And then perhaps the next major change comes along in about 200 years' time, when you have William Herschel splitting sunlight through a prism. And he's measuring the temperature of each of these colors. And what he discovers, that when he moves his thermometer beyond the red, he still registers a temperature. And he discovers that there is light beyond. It's not just objects that are invisible to the unaided eye, but there is light that is invisible to the unaided eye. But it behaves the same way. It's still radiated, refracted. It follows all the same patterns of light. So there are more colors that we can see than we can see with our unaided eye. And of course, now we use all those forms of light. Herschel discovered infrared. We now know the whole spectrum extends up to ultraviolet, to X-rays, gamma rays, down to infrared, microwaves, and radios. And if you like, these are all just different colors of light. The colors that we can, the thing that distinguishes colors are wavelength, the wavelength of the light. And the colors we can see with our unaided eye, blue, it's got wavelength of, say, 40 thousandths of a millimeter, red about 60 thousandths of a millimeter. But the full spectrum takes you down to wavelengths of thousands of kilometers in the radio, and in the X-rays, wavelengths that are a tiny fraction of the size of an atom. And all these different lights tell us different things about the objects emitting them. For example, you can also think in terms not just wavelengths, but in terms of energy. Beyond the red, you've got low energy emission. That comes from very cool regions of the cosmos, diffuse gas clouds in between the stars. You also get high energy radiation, ultraviolet X-rays. That comes from very hot stuff, most explosive and violent events in the universe. So these are all quite complementary. We use all these lights now. We use telescopes. We see beyond what is available to the unaided eye. And we, of course, have changed our whole perspective. 400 years of the telescope have taught us that Earth isn't at the center of everything. And in fact, we're truly insignificant. Our planet is just one of probably millions of planets in orbit around hundreds of thousands of millions of stars in our galaxy alone, which is one of several 100 billion galaxies across the universe. So we no longer occupy that special space. And indeed, one of the most important things that we have learned over the last 400 years or so is that the stuff that we observe through our telescopes is only 5% of what is out there in the universe. Here's your obligatory cosmological pie chart. So what we see through our telescopes is ordinary matter, stuff made of baryons like us, stuff that reflects or radiates light. Since probably almost like 100 years, we've been well aware that there is other matter out there. This is the dark matter, that it has mass and it has gravity. We know it's there because even though it doesn't interact with light in any way, hence the name dark, we can see the effect its gravity has either on the shape of space or the way it pulls around objects that are light emitting. And then since the turn of this century, so the late 90s, early noughties, we now know there's another 70% of the universe that we call dark energy. We have even less idea what this is. But again, it's invisible. That's what the dark is. And it's called energy because it's like a force field, and it's one that pushes, unlike gravity, which pulls together. And this is our complete vision of the universe. So we have a double whammy. First of all, we're not only just dependent on light for our views of the cosmos, but with that light, we are only directly sampling 5% of what's out there. Through all this time and all these developments and everything we've learned, I would say they've been driven by advances in telescopes and detectors and opening up new wave bands, and all of these will open up new discovery space. And indeed, it seems that observations really drive the science. And I can think if it's done that for 400 years, you can guess it's going to continue to do that over the next few hundred years as well. So in this talk, I want to try and get you enthused and excited about the next generation of amazing facilities that will be coming online in the next decade, potentially 2 decades' time. I want to talk to you about the science they're going to enable, and indeed, how they may even change the way we do our science altogether. And here's just an array of some of the things I'm going to be talking about. But when you design a telescope, you're really looking for it to do exactly the same thing, just better, than the unaided eye does. If you think about what you want from your eye is just the same as what you demand from your telescope. First of all, you want to collect as much light as possible. You want to see that over as wide a field of view as possible. You want to collect as many colors as possible. And here I'm taking colors right down to radio and up to X-rays. You want to see everything in focus. You want to be able to see fine details. You want to be resolved structures. And not just that, you want to be able to detect any changes that might happen with time. And that's really what we demand from our telescopes. So I'll start with the first. We want to collect as much light as possible. Now, why is that crucial in astronomy? The problem is that the universe is actually fairly faint. And if I've got a distant galaxy or stars that I want to observe, I can't just turn up the light to see it better. I have to collect more photons from that particular object. And for astronomers, if something is further away, its light gets diluted by the square of the distance, towards us. And the distances are so immense that you can have objects in incredible distance, and that means they're incredibly faint. And the other thing, because the distances are so large, the fact that light takes a finite time to travel becomes important. That means if you see a galaxy that is at a colossal distance away, that light takes 6 billion years to travel from there to us. We're seeing as it was 6 billion years ago. So the more distant objects you see, which are probably the more distant, are also you're seeing further back in time. So we're enabled to collect samples of different epochs through time. And of course, with any population, the fainter objects are far more numerous than the dramatic bright examples. So if you want a representative sample of any epoch, well, ideally, you want to get the faint objects and not just the dramatic bright ones. So how you do that is you have as large a collecting area as we can. Now, we tend to talk about telescopes as being light buckets, which means you're basically catching the light. And the way to think of this is you imagine photons, almost like raindrops, falling in your garden. And you will collect a lot more water in a paddling pool size aperture than you are in a coffee cup you left out on the bench outside. And the same thing is true about telescopes. With an 8-meter diameter telescope, you collect a lot more photons than will fall into the sort of ½ centimeter of your eye's pupil. So telescope aperture, and that gives the size of the mirror or the lens that is used, isn't crucial. And that's why the size of the telescope is usually included in its name. The biggest telescopes nowadays that are in use have mirrors that are 8 to 10 meters across. This is the Very Large Telescope in Chile. 4 telescopes, each with an 8-meter aperture mirror. And there's the 10-meter Keck telescope, where you achieve the 10 meters by hexagonal tiling of smaller mirrors. These are the best in action now, but the next generation of telescopes are going to go up to apertures of 40 meters, and with suitably astronomical budgets as well. And there are 3 that are definitely in the offing in the near future. There's a Grand Magellan telescope. It's under construction, so this is an artist's impression, but it's in Chile. It'll come online in 2025. Instead of just having one of these 8-mirror telescopes, it's got 7 of those 8 mirrors, mimicking up a diameter of 24.5 meters across. There's a 30-meter telescope, which, not surprisingly, has an aperture of 30 meters. And that's made from tiling just under 500 1-meter mirrors together very precisely. This is due to come online in 2027. And then the granddaddy of them all is the extremely large telescope. We're very imaginative with our names. And this is going to go up to 39.3 meters across. You're going to have 800 of those mirrors tiled together. And this is under construction in the Atacama Desert in Chile. And this will buy you 250 times the light-gathering power of something like Hubble Space Telescope, and the image will be 16 times sharper. So what does this buy you? It gets you more distant objects, it gets you further. Big telescopes like this look in detail at pointed observations of the sky, and they stare for a long time. This is a very deep picture of the universe to distant galaxies that was taken with the Hubble Space Telescope. And you can see galaxies, as I say, at a range of epoch. The nearest ones are maybe 1 billion light years away, just this bright yellow one here. And the more distant ones are up to 13 billion light years away. That means the light is taking 13,000 million years to get to us. And if you compare nearby galaxies, which kind of look like the galaxies in the nearby universe, to ones that are several billion years ago, well, they look different. They're kind of blobby, and they're smaller. And they're blue, which suggests there's ongoing star formation. And some of them are sort of elongated into sort of chains of segments. And we think we're seeing galaxies evolve and change with time. And here these picture shows that perhaps smaller fragments, smaller galaxies, are assembling to merge to form today's big galaxies. And the most distant galaxies we can detect, well, the number of truly distant galaxies that we've discovered are still fairly small. And these are some of the furthest that we've managed to detect so far. And these are, because they're so far away, they're early galaxies, and they're intrinsically small, perhaps a few thousand light years across, maybe only 1 million stars in. So they're intrinsically small, intrinsically very faint, which makes them that harder to pick up. So not only are they inherently less luminous, but because they're so far away, they're moving away from us at great speed by the expansion of the universe, and their light is shifted towards the red, which is why they all look red. But the problem is, even with the best telescopes currently, if you are here on the left-hand side, and this is looking back in time towards the Big Bang on this side. The furthest galaxies we see date to when the universe was about 400 to 500 million years old. And we still see them as galaxies. We are not seeing the very first galaxies. We're not seeing galaxies in the stage of forming. And that's what a lot of this excitement about large aperture telescopes is going to bring us. The other thing you notice is that these are blobby, as I say, and that's going to be crucial also because you don't just want to detect them, you want to do science with these images. You want lots of photons in each blob so you can compare where star formation is going on, relative sizes of blobs. You want to be able to resolve detailed structure. So the second thing a large telescope enables is the way you can resolve our, targets. Now, I promise you this is the only equation in tonight's talk. But theta is just the angle by which you can resolve two objects as separate things rather than they're merged together. It's like an angular separation. So when you can resolve, that's a blur, and then they separate out into different objects. So the smaller the angle, the closer detail that you can see. And it's related to the wavelength of the light and the diameter of the telescope. So for any wavelength of light, a bigger diameter gets you more of this detail. You get this much sharper detail. Now, this is a theoretical best for any telescope. You're limited by the fact that light wants to spread out in a process called diffraction. And this is as good as you can get. You don't achieve it. We won't achieve it with these telescopes I've just been describing because they're based on the ground. If you really, really want to get the best resolution, it's a very expensive option, is you go into space. And this is why the Hubble Space Telescope is so brilliant, or is brilliant once it was fixed. It's not because it's inherently a large mirror. Just to show you, these were the 8-meter, 10-meter telescopes I was talking about. It's got a very small diameter mirror. It's only 2.4 meters. But because it's out in space, you're not seeing the light as it's traveling through the atmosphere. And that's the limit for the ground-based telescopes. Any light to get to you has to travel through the atmosphere. And the atmosphere is moving around this turbulence. And that smears out the light rays while you're gathering the data. And you get blurred images. You can only get around that if you go out above the atmosphere. Hubble was launched in 1990. It's been a fantastic success. It's now limping along on fewer gyros than we would like. So what comes next? There's a James Webb Space Telescope. This has got 18 hexagonal segments, making up a mirror 6.5 meters across. That's almost like 3 times bigger, wider than the Hubble Space Telescope. Now, it's due to be launched in 2 years' time. I'll believe it when I see it. It's in storage at the minute and currently eating a lot of NASA's budget. When it does launch, again, it'll have 100 times the sensitivity, 100 times the resolution detail that Hubble Space Telescope offers you. You do have a problem. If you've got a 6.5 meter mirror and you've got to launch it into space, well, you don't get nose cones that are 6.5 meters across. You have to fold up this mirror into the nose cone. It then launches into space, and then that mirror has to unfold in situ. And the problem with this is the James Webb Space Telescope is not just going into an orbit around Earth, it is instead traveling much further away. 1.5 meters, sorry, 1.5, that's very close, 1.5 million kilometers beyond the Earth. And that means they put it in that location because it can then block the light of both the sun and the Earth with a large sun shield. So the first thing that opens out in this sort of pink silvery thing is a sun shield. And then the mirror opens out. And it needs that sun shield because this telescope will operate in the infrared, in red and infrared. And you've got to keep it at temperatures of about minus 220, or else the telescope itself is radiating in the infrared and producing that kind of background glow. But the advantage of this is, especially by going to the infrared with this extra collecting area, we will be able to see further back in time. This is where I said we could go to the current limits. We can now expect with the James Webb Space Telescope, we will go back to perhaps 200 million years after the Big Bang and start witnessing the process of those very first galaxies forming. James Webb will be shortly followed by WFIRST, which is another infrared telescope. And the difference to this is it's not that big, mirrors the same size as the Hubble Space Telescope, but it looks at a huge range of sky. This is a survey telescope. And one image from this has got about 100 times the size of a Hubble image. So this is going to survey the sky, and it'll find things that James Webb Telescope will follow up in detail and characterize. And surprisingly, it takes so long to plan and build and design these telescopes. NASA are already thinking about what comes next in the 2030s, 2040s, and the one after that is nominally called LUVOIR. Due for launch about 2040. It's not just going to work in the red and the near-infrared, it's going to work in a whole host of wavebands. And currently it's either going to be 8 meters or 15 meters across. So this is kind of planning well ahead for the future. If you like, this is going to be a super-duper Hubble. That's probably the best way to think about it. But that's a way away in the future. Now, these telescopes are going to be exciting not just for looking at those very distant galaxies in the distant universe. They're going to revolutionize our understanding of the nearby universe in great detail. So, for example, one of the things I mentioned slightly earlier is the fact we now know that almost every star in our galaxy probably has a planet in orbit around it. And one of the key aims of things like the James Webb Space Telescope and WFIRST is to look at those planets around other stars in more detail. We already know of about 4,000 planets. There's a telescope that was launched last year. It's called TESS. It's expected over the next few years to add another 20,000 planets that we know of around nearby stars in our galaxy. This will find them, and then WFIRST and JWST will be able to image the exoplanets. Now, we're not going to have fantastic views of them like we have planets in our own solar system. They'll just be a dot. We can look at the color of that dot. We can see how the color changes. Perhaps we can start telling something about whether, cloud or weather patterns on it, and how it changes. But also, more than that, when we have these super-duper telescopes, we will be able to start characterizing the atmosphere around those planets. This is something we already do. It's very expensive in Hubble Space Telescope time. We'd like to do it in more detail for more planets. But imagine you have a planet that as it goes around its star, every so often it passes behind and then it moves directly along this line of sight between you and the star and blocks some of the light. This is called a transit. What you can do with these observations, or these kind of objects, is you wait till the planet is just in front of the star. Now, it's going to block some of the star's light, but some of that star's light will be filtered through the planet's atmosphere. And as that light interacts with the molecules and atoms in the atmosphere, they will leave spectral features that reveal the constituents of that atmosphere. And there are more molecular signatures in the infrared than in the visible. So the JWST will be able to determine perhaps the chemical composition of smaller planets than we've been able to do so far, perhaps getting down to Earth-sized planets or perhaps super-Earth-style planets. And we even have the potential to, if we can ever agree on what a biosignature is, that we might be able to look for biosignatures around distant exoplanets. Just out of interest, this is an exoplanet that's been observed with the Hubble Space Telescope for this graphic. And here you can see it's got water vapor, probably steam in its atmosphere. It's also got titanium oxide, which is one of the key ingredients in sun cream, right? So a planet with sun cream clouds and atmosphere, strange. But not only will we get to see exoplanets in detail, we expect to get a much better understanding of star formation. Because after all, star formation is what underpins the structure of a galaxy and also how that galaxy evolves and changes with time. And the trouble with star formation is it's a hidden process. Where gravitational collapse is going to happen is where stuff is very dense and cold. And usually that means it's quite dusty and opaque. So perhaps within these sort of cold gas clouds in our galaxy. Using infrared, you can peer through the dust. Infrared light travels through dust because it's less scattered. And you can see into those clouds. Now imagine being able to do that in a range of infrared wavebands at high detail. Our problem at the minute is star formation is completely hidden from view. We can model it in our computers, but in practice, it all goes on within these clouds, and you just suddenly get this ta-da moment when the young star breaks forth, sometimes to begin with these enormous jets, and breaks out of its cocoon. If we can see into the clouds as the stars form, we'll get a better understanding of what physical processes at play, what is important about a cloud that tips it into star formation, what's the mass of the stars that emerge, how do you know whether you've got a singleton or a binary system? So we'll unlock the process of star formation. And not just star formation, but planetary formation. This is the Orion Nebula coming to a night sky close to you tonight. It's in Orion's sword. And from the Hubble Space Telescope, this is full of really young stars, less than 1 million years old, some of them less than a few 100,000 years old. And some of these stars, as they emerge, if you like, fully formed, they're surrounded by thick, opaque cocoons that block the light of the underlying star. Now, these are the observations. This is the artist's impression. And this is material that didn't get used up in the formation of the star, but settles in a thick, opaque torus. And it's within that dusty torus that young planets start to form. Now, we are beginning to detect these. These are going to be a challenge even for James Webb Space Telescope. But we might see the process of planetary formation as it moves from these thick dust toruses over perhaps a few tens of millions of years to the star burns brighter, it has winds, it clears a lot of that disk, and the disk settles down to something very thin, and the planets are forming within that disk. And they form first by particles sticking together with electrostatic forces, and then crashing together by gravity and collisions, and you build up planets within this disk of dust and gas and little rocks and ice. Now, this is the artist's impression. You can see there's maybe a planet there, maybe a planet there. And as they go through the disk, they kind of carve a ring or a gap as they accumulate material as they go through the disk. This may be the artist's impression. This is the real thing. Now, this is one of the most famous ones. This is a star less than 1 million years old, one of these debris disks, where you can see the gaps forming in the disk as the planets are collating together. And here's a host of other ones. These images were taken down beyond the near-infrared in the sub-millimeter by an amazing telescope called ALMA. Okay, just to go back a minute. The other thing about the sub-millimeter is that you're not just looking at the structure of the disk, but you can look at the chemical composition of this disk. You can find out, if you like, what the raw ingredients are in the disk and the raw ingredients for these planets. Now, even if you move down into radio wave bands, you've got the same principle that a bigger dish, in this case it's a dish rather than a mirror, allows you to see more structure and more detail. The problem is that the wavelength now has grown much longer. So if you want really good resolution, you need a very big dish. And these dishes are 7 and 12 meters across, but you can't build a big enough radio antenna to get the resolution. So what we do in radio wave bands is a very clever process called interferometry. And that's where, in the case of ALMA, you have 66 of these antennae that you arrange to mimic up one very much larger telescope. And they all observe the same source at the same time. The data are collected and collated to within like a trillionth of a second. And you just make it up to be like a large telescope. And you just saw them moving the antenna around on a transporter. You can move these around and you can juggle how much the sky you see and how much structure you see. It's adjustable. Now, we already do this kind of technology in ALMA and in other radio telescopes, including the ones down Barton Road. This technique is going to be used in 2 forthcoming very ambitious projects. There's the Square Kilometre Array, which is going to be the world's largest radio telescope. The name gives it away, okay? It's going to have a collecting area of 1 square kilometre, which means it's going to have thousands of these larger dishes. They're up to about 15 meters across, and millions of these smaller antennae. And they're going to be located in very radio-quiet places in South Africa and Australia. But by increasing that diameter of the effective telescope, you're going to start matching the radio images we get to the same detail you see in the Hubble Space Telescope. So we'll be able to match the radio to the visible data. This will, again, you see a range of colors, far greater sensitivity than anything we've got currently. This is still in process, it's still in design and testing the technology. It's expected the construction won't begin for another 5 years, and observations will begin probably in about 10 years' time. But this kind of telescope, when you move down into the radio, you're susceptible to cold stuff. And here I mean like cold molecular gas, neutral atomic hydrogen, first of all, that lies between the stars and a galaxy. When you look at a galaxy in the visible, you're seeing the structure as determined by stars that give off the visible light. And in between these stars in the interstellar medium, there's diffuse, cold, neutral hydrogen gas. If you look in the infrared, the radio, this is the visible, you start to see where the gas is between the stars. And by mapping this both in our galaxy and in distant galaxies, we can see where star formation is going to happen before it happens. Okay, so it's tracking back where star formation will occur in a galaxy. And also, how does star formation differ in our galaxy to other galaxies, and understanding that process. And it's going to tap into cold gas, not just in nearby galaxies, but right back at the very early stages of the universe. So if we go back to the kind of schematic, except now it's sort of stretching another way up, you were here at the bottom of the screen, about 13.8 thousand million years after the Big Bang. A crucial event happened when the universe was 300, 400,000 years old. And that's when it stopped being like a hot, complicated soup of charged particles that wouldn't let photons escape. And by then, the universe had cooled and expanded that the first atoms begin to create. And at that point, the universe stops being completely opaque, and light can travel through it. It's completely transparent, and light can stream across the universe. The problem is, it's still dark, because this region, which is sort of described here, say, the first few 100 million years of the universe, that's when the very first stars and the very first galaxies begin to form. Now, we can't detect these directly. Go to the first stars, for example. We expect they're going to be very, very massive, perhaps 100 times the mass of our sun. Now, these will be very short-lived. We don't expect to see them, but what we might be able to see is their effect in their environment, because they'll be very hot, very luminous. The light from these stars will go out and break apart the atoms in the vicinity. That's what we call ionizing the gas. And so these stars will grow ionized bubbles. And as you get more stars and bigger structures building up, these bubbles will expand and begin to overlap. So you change the nature of this cold gas from being completely neutral to being ionized. And if we can track that change with history, we may not see the stars, but we'll directly work out when it is these first structures will start to emerge. And this is one of the prime drivers in the whole design of the square kilometre array. And then you can take this to a much bigger extreme. The very biggest diameter you can mock up with a radio telescope is the diameter of the whole Earth. And this is the ethos behind the Event Horizon Telescope. It's a much sparser sampling. There are 8 large radio dishes in remote locations as far as Hawaii and even down at the South Pole. But they're observing in the millimeter waveband. And if you increase this resolution, or increase this diameter, you get down to a resolution such that you would be able to detect a grapefruit on the lunar surface from Earth. Really impressive. And that is, well, we don't really think they're grapefruit on the moon that we're going to look, but that size is almost exactly the same as the size we expect from the event horizon, both around the black hole in our own galaxy. Now, this is the nearest a supermassive black hole to us. It's 26,000 light years away. It's a long way, so don't worry. It lies within the star cluster right in the center of our galaxy, and it's got a mass of about 4 million times that of the Sun. And this Event Horizon Telescope spent 10 days in April 2017 staring and observing that black hole. And also the supermassive black hole 55 million light years away in this giant galaxy. And this is a much larger black hole, 6 billion times the mass of our Sun, and so is expected to be bigger. Now, what I mean by bigger is we're not going to see the black hole. Remember, light can't escape from the black hole, hence the name. What we're actually going to observe is what we call the event horizon around the black hole, the size of the event horizon. This is, if you like, the danger line, beyond which you cannot see any events. And it's well matched to the expected event horizon around both these black holes. We won't see it as such, but we expect to see it. I mean, this is going to just be a simulation, but likely to see its silhouette, if you like, its shadow, as it moves across the background glow of the galaxy. And it's expected that actually resolving the shape, we can test it against quantitative predictions about, what we predicted, the black hole of a certain mass or a certain spin is visible. And if these are successful, we will extend it to other supermassive black holes. Now, obviously, this is very complicated. The results aren't out yet. It's so difficult to correlate all these data. I'm hoping they'll be out probably next month or the month after, though I feel I've been saying that for the last 6 months. But soon, we will see those results. But this is very difficult to do. And typically, when we want to study the environments of black holes, we don't use large radio dishes like this. We use X-ray telescopes. And this is good for black holes of all sizes. And you're not seeing the black hole again, but you're seeing material. Okay, artist's impression, by the way. You were seeing material just before it's swallowed up and disappears over the event horizon, where it jostles and it gets very hot. And in the vicinity of this event horizon, you have X-rays being produced. And X-rays are the most energetic light there is. They're being produced closest to the event horizon. So this is a way to sample relativity and gravity at extreme, about the most extreme conditions we can get. We can see the accretion process, also the jets that are launched from these black holes. And these jets are important, by the way, because we think nearly every galaxy has got a supermassive black hole at the core. And these jets plow out of the black hole, and they carry energy out into the galaxy and maybe beyond. And you're pumping out energy that can heat up clouds, that can stunt the star formation, and perhaps affect the growth of the galaxy around the black hole. So these black holes could be important also for galaxy growth. And the step change for that, I mean, there will be smaller X-ray missions launched, but the big change is going to be Athena, which is the European Space Agency X-ray telescope, due for launch in 2031. And it's going to be 100 times more sensitive than any X-ray telescopes we have now. And even though the telescope is a different kind of design, the principle of larger collecting area will get more photons of light. So we will see more distant black holes. We will trace black hole activity at the centers of galaxies out to much more distant galaxies, and perhaps regions where that accretion process is far more intense than we see in nearby galaxies, and begin to map its role perhaps in the buildup of galaxies. And the thing about black holes is their brightness, their power output, that is produced by the way matter falls through gravity. And so they're being powered by unstable flows of material. So they don't have a steady brightness. The X-rays from black holes will flicker and pulsate and be highly variable, change in timescales of weeks to months to years. So one of the nice things is, if your favorite source goes into outburst, you want to be able to observe it while it's doing something really interesting. So Athena will also have the capacity to respond to news that a source is in outburst, and then just swing round and immediately observe it and follow it up. And this rapid response time is becoming an increasingly important part of astronomy. Because high-energy radiation is not just released from black holes, it's also released from transient events, one-off events like when a star reaches the end of its life and it undergoes a massive supernova explosion, or things like gamma-ray bursts. And we need the ability to respond to these transient events. And this is going to happen with robotic telescopes. I'm introducing the Large Synoptic Survey Telescope. Artist's impression, it's not built yet, but it is being built. And this is a large mirror. It's 8.4 meters across, but it's not going to stare at one part of the sky. It's got a massive camera on it that's going to, so one of its images will be equivalent to 3,000 Hubble Space Telescope images. And with this massive camera, it will be able to image the entire sky available to it twice a week. And you have a survey telescope that is just mapping the whole sky, and then very sophisticated software that instantly analyze and corroborate the data, and they're looking for changes. And it could be changes in brightness, or in color, or maybe things moving against the fixed backdrop of stars. So this is time domain astronomy. This is a new thing. We're looking to follow up on instant changes. And this is important, say, for detecting dark asteroids that might threaten the Earth, or even interstellar asteroids. Just a couple of years ago, artist's impression, Oumuamua was the first interstellar asteroid that we had discovered falling through our solar system. We know from its velocity and its trajectory, it's not something that originated in our solar system. Instead, it's some shiny, rocky fragment that was torn off another solar system somewhere in our galaxy, and then sent, coursing through space, and it just happened to fall in and plow through the core of our solar system. Now, we can't observe this anymore. We only discovered it just as it was receding away from Earth. We can never catch it up. But as expected, the LSST will discover many more of these interstellar asteroids within its first year of operation. So if we do start to detect them, first of all, it tells us more about how common these are, and that tells us something about how they're torn from other planetary systems. But we might have the possibility to rendezvous with some of these if we have enough advantage, enough notice, and see perhaps what something from another solar system looks like. We'll also see explosions. Again, that very quick response time enables us to see when stars go supernovae in distant galaxies. So the before pictures are down below. These arrows point to where stars have exploded in very distant galaxies. And in that moment of outburst, they can outshine the entire galaxies. Now, supernovae are very important if you want to map the expansion of the universe. There's a particular type of supernova that comes from a transfer of mass from one star to another in a binary system. And that means we understand what happens, we understand that light's given out, and we use them almost as tracers as to how far they're away and how fast they're moving away from us to trace that expansion of the universe. And it's from such supernova we discovered that the universe is expanding, and that, well, not just expanding, but that expansion is accelerating, and hence the need for dark energy. Now, these are rare. They happen on average about 1 per galaxy per century. We're going to find a lot more with LSST. You don't just happen to be looking at the galaxy by chance. We can survey the sky and probably start detecting about 100,000 of these a year, and we'll begin to be able to unpack perhaps different theories for dark energy. Now, I kind of lied at the beginning, right? I was a little bit dishonest when I said that light was all we have to work with, because that has changed. And that has changed over the last few years in that we are now able to detect gravity directly through the detection of gravitational waves. And these are not waves as light waves, but traveling ripples, traveling distortions of space that will stretch and squeeze in orthogonal directions. And these are emitted for when like 2 black holes spinning around each other accelerate and merge. And the frequency of the gravitational waves will increase, and you get a signal like shown here at the left, which is a sort of rapid chirp. And we detect them by looking for that stretching and squeezing. Down here, you have one of the LIGO detectors. You have 2 arms, and you want that this is stretched while this is squeezed, and you're looking for that kind of signal. But on a distance scale of a 4-kilometer laser beam, changing its size by less than a millionth of an atom. So you see why it took us so long to detect them. We are now beginning to discover these. There was an upgrade announced just a couple of weeks ago that Advanced LIGO is going to now detect perhaps 3 of these a day by 2024, perhaps see black hole collisions twice as far away. And what's interesting is in blue are the black holes so far detected by gravitational waves. In purple are the ones that we tend to see in X-rays. We're seeing a new flavor of black holes, much more massive ones than we routinely detect through the X-rays. So we'll have much better statistics and kind of progenitors and mass and spin and understanding of these processes. But you know, these are still quite small black holes. We all like the supermassive ones that live at the centers of the galaxies. And we know those galaxies sometimes collide and merge. After all, we see it way back in the universe. We see it in the nearby universe. Imagine 2 spiral galaxies. Over several hundred million years, they merge and collide. And if they've each got a supermassive black hole, what happens if those 2 black holes collide and merge? Well, we expect colossal release of gravitational waves, but the time scale is longer. 2 stellar-sized black holes collide and merge over a period of sort of milliseconds. 2 of these colliding will take the signal we received over 1,000 seconds. And that change of frequency means we won't detect them with these tiny laser beams. We need laser beams measuring distances that are over 1 million times longer. So the next generation of gravitational wave detectors will be out in space. Here's the concept for LISA, European Space Telescope, European Space Agency satellite, or its constellation of 3 satellites. And it's due for launch 2034 or so. And they travel they follow the sun around they follow the Earth around the sun, okay, heliocentric solar system, not geocentric. But they follow about 50 million kilometers after the Earth, and they're looking, again, for distortions in the length of the laser beam. But these laser beams are about 2.5 million kilometers long, okay? So this is a colossal technical challenge. And it's clear to say that detecting gravitational waves from such events is really majorly exciting in its own right. It gives us a new way to look at the universe. But it becomes truly transformational when you can detect gravitational waves and radiation from the same event. And this happened for the first time in 2017, where 3 different gravitational wave detectors detected an event, and 1.7 seconds later, 2 gamma-ray satellites detected a burst of highly energetic gamma rays. Now, both the detectors on the ground and in space, they don't have good resolution. But you could triangulate and say, okay, it's going to be in that patch of the sky. So some event happened somewhere here. And they sent out an all-points alert. And so everybody with an optical telescope turned and said, is there any change that's happened in that part of the sky? And with 11 hours, observers using Los Cumbres Observatory found a galaxy where there was a new event that had happened into it. And this was the first observation of an event which had been hypothesized. It's called a kilonova. That happens when 2 neutron stars collide and merge. And it showed that this could be a source of these short gamma ray bursts that we don't otherwise have a clear idea of how they're producing these waves. And this was likened at the time by one of the astronomers. So you see light and gravitational waves. It's like seeing the lightning that accompanies the clap of thunder. And these are complementary bits of information. The gravitational waves tell you about the masses and the motions involved in an event. But the electromagnetic radiation in any waveband tells you about the physics, the astrophysics that's going on in the event. And this is called multi-messenger astronomy. And it's not going to stop there. There are other pieces of information that we are beginning to use. And amongst them are cosmic rays, which, unlike what the name seems to suggest, these are not beams of light. But these are actually direct samples of matter that are coming from the universe towards Earth. They are electrically charged particles. And they just happen to stream our way. And they stream away at an enormous rate. You reckon probably about 10 to 100 cosmic rays are passing through your body this very second. Okay? There are lots of them. And some of the really exciting ones are traveling at speeds close to the speed of light. Extraordinarily high energies are required to produce, some kind of event. It's got to be incredibly energetic to produce these kind of sources. So we do detect them. These high energy ones we're very excited about. You don't detect them directly because they come into the atmosphere and then they interact with the atoms and molecules at the top of the atmosphere. So they don't make it to the ground, but they produce a shower of secondary particles which are detected by detectors down at ground level. And then you use the simulations to build back up to the properties of the primary particle that instigated that shower. This is an image of the state-of-the-art at the minute, which is the Pierre Auger Observatory in Argentina, that covers an area of 3,000 square kilometers, measuring for these cosmic ray events. Now, we don't get nice images, and also it wouldn't help because these are charged particles. They're not going to travel in a straight line from A to B. They're being scrambled by any magnetic fields along the way between us and the source. But detecting them and the kind of cosmic rays tells us about the physical processes going on in galaxies and events where you are accelerating such particles to the speed of light. And then the fourth part of this puzzle is neutrino astronomy. And this is also very exciting. Neutrinos are almost massless particles. They're electrically neutral, and they travel at the speed of light. And the exciting thing about them is they're emitted from nuclear reactions. So it could be from nuclear fusion at the heart of stars, it could be radioactive decay, it could be what's going on during the implosion of a supernova. And why that's exciting is neutrinos they don't interact with matter, or only very weakly. They travel through things. So that means they can escape from those very dense environments from which they were produced. Now, we can't yet, but if you could see the whole sky in neutrinos, you would get a completely different picture. Light comes from the surface of objects. You're just seeing the surface of objects. With neutrinos, you can see right to the heart of where the source is being produced. So right in the heart of stars, as I say, in the core of that supernova implosion. So we get a completely different, completely alternate view to the normal view of the universe. And they're also likely, especially high-energy neutrinos, they're going to be produced in highly explosive, violent events. But of course, what makes them exciting, the fact they only weakly interact with matter, makes them very difficult to detect, because they travel straight through Earth again. And how you detect them, well, it's quite a clever way of doing it. This is the Icecube Observatory, which I always think looks rather like a very good James Bond villain lair. This is located in the South Pole. Now, this is not the detector. The detector is under the ice, where they have 86 strings, long strings, that are buried in the ice, and each has about 60 sensitive light detectors on. So you drill holes in the ice with hot water, and then you have to hurriedly stuff the string down before it all freezes and it doesn't get quite to the depth. But this is one of the strings in the light detector. And these sample a full cubic kilometre of ice, really pure transparent ice. And those sensitive light detectors are waiting for just that brief flash that might mark a very rare occasion where a high-energy neutrino bumps into the nuclei of the ice atoms. And with 5,000 detectors and the different arrival time to each detector, you can map back the direction and the speed and the energy of that neutrino. And this has already proven effective at discovering perhaps over 100 really fast-moving, highly energetic neutrinos, some of them moving with about 100 times more the energy than anything we can produce in the Large Hadron Collider, for instance. Having proven this in principle, neutrino astronomy is a new face of astronomy, and Icecube will be upgraded to Icecube Generation 2 in the near future, where now they know how transparent the ice is, they're going to include about 120 new strings at a deeper, wider spacing. But that will enable them now to have a collecting area, so they'll sample a space 10 kilometers cubed of the ice, and they can expect an order of magnitude in detections of neutrino rates. And with that kind of thing, and you correlate that with the visible light, so if there's an event that goes off, does it produce a burst of neutrinos? Because neutrinos travel at the same speed as light. So do you have correlated events? And eventually, we might be able to get statistically significant samples that align with different sources. Just to say, okay, that's the original Icecube, and that's just part of the wider extension. So I've given you just a very selective sampling of all the new missions and facilities that are coming online in the next couple of decades. And I've only been able to touch on some of the examples of science that we expect to emerge. And indeed, you can fully expect that all our ideas on a whole diverse range of topics, from architecture of planetary systems, out to how galaxies are born, out to perhaps how the eventual future of the universe, all of these are going to have to be updated by this continual stream of new data coming in. But the last point, of course, is the most exciting thing about any new facility, any new telescope, is not the things you expect, but the things you will discover that you had not possibly anticipated. And so there is always that potential for a whole wealth of discovery that we have yet to even guess at. So I think we're coming up to a very exciting time in astronomy. I'm certainly looking forward to seeing the results from all these missions and telescopes, and I'm really looking forward to the kind of things they're going to discover, and as I say, how they're going to change the way that we do our science. Thank you very much. Thank you.
Thank you very much indeed, Carolin. That was just amazing, amazing. I mean, it's extraordinary to be able to see so much detail of bodies and things in our universe that are so distant. The scales are so huge and the times are just so great. And with so many new plans for new telescopes, new experiments, just fascinating to hear about some of what may be discovered or is hoped to be discovered. But of course, the particularly exciting thing, as Carolin's just said, is the sort of the unknown unknowns. So I think we better plan to ask you to come back in 10 years' time and tell us what some of these new telescopes have discovered. So thank you very, very much indeed. So next week, the subject changes again. Professor Andrew Blake, who is formerly Director of Microsoft Research here in Cambridge, and now Chairman of Samsung's AI, Artificial Intelligence Research Centre here, is going to lecture on computer vision. So I hope to see you then. Thank you.